Good afternoon, everyone, and we are extremely sorry for this delay due to some technical glitch. And welcome to the fourth lecture of our online lecture series. This is Juma Ghosh, curator at Nehru Science Center, Mumbai. We are holding this week-long lecture series where we are helping the students to explore various career opportunities in future if they choose to work in the frontiers of science. Today's speaker, Dr. Ramya Sethuram, will be talking about the future opportunities for Indian students in TMT project. Let me take this opportunity to introduce Dr. Sethuram. Dr. Ramya Sethuram is a project scientist at India TMT Center at the Indian Institute of Astrophysics, Bengaluru. After completing her PhD from Indian Institute of Astrophysics in galaxies, she did her postdoctoral research work in Paris and Shanghai Astronomical Observatory. Her research area is galaxy formation, evolution. Her research interests are mainly on the low luminosity galaxies, stellar populations, and star formation histories in the dwarf galaxies. Also, she is interested in astronomical instrumentation as well. With these words, I'd like to thank Dr. Sethuram for accepting our invitation for this lecture, and I want to hand over the mic to her.
Hello, can you hear me? Thank you, Juma. Let me share my screen. Can you see my screen? Yeah. Uh, is this okay now? Yeah. Thank you. So I take this opportunity to thank Nehru Science Center, Mumbai, for giving me an opportunity to speak about Mega Science Project, the 30-meter telescope project. I'm very happy, privileged, and honored to give this talk in the Women's Week, celebrating Women's Week. So, the title of the talk is Future Prospects for Indian Girl Students in Mega Science Project. I'm working in the 30-meter telescope project, so I'll be able to say a few things about 30-meter telescope and then the opportunities it provides to the girl students. So my name is Ramya Sethuram. I am project scientist at India TMT. So let me first give you a brief overview of what is 30-meter telescope. 30-meter telescope is an international project. It's a project to build a large, extremely large telescope. The five institutes or the five countries involved here is the Caltech and University of California in US, Canada, Japan, China, and India. So the coordinating institutes within India for this particular project are ARIES, IIA, and IUCA. ARIES is at Nainital, and it's also an observational institute. IIA is in Bangalore, and IUCA is in Pune. The funding agencies for 30-meter telescope project for India are the Department of Science and Technology and DAE, and we thank them for the opportunity. So what is 30-meter telescope? What you see is a cross-sectional view of the 30-meter telescope over here. And this is a huge structure. The height of this structure is about 60 meters. And this is almost equivalent to the Qutub Minar situated in Delhi. So this is such a huge structure. This is a telescope. It is going to be an optical and infrared telescope. Sharp images of objects, celestial objects. The range of objects could be anywhere from our solar system objects, like our planets and its moons, to very farthest objects visible in the universe. That is the first stars and first galaxies. So how is it able to do that? Because it has a primary mirror of a huge size of 30 meter in size, I have given here a few numbers. So it is having a very good spatial resolution. So it is able to resolve almost 12 times better when compared to Hubble Space Telescope, that is the HST, and when compared to Keck, which is a 10-meter size telescope, it is 3 times much better in resolution. And when I say resolution, I have given a small equation here how we calculate resolution. It is with respect to the wavelength of choice. That is, if we take a 1 micron wavelength, then d will become the diameter of the mirror, which is 30 meter, and theta will give the resolution. So this resolution will tell us how finely we can separate two objects which are close by. And this particular quantity is 12 times better when compared to the Hubble Space Telescope. So similarly, sensitivity, the parameter here goes as the uh, fourth power of the aperture of the telescope, that is the diameter of the telescope, and this is in case of adaptive optic system. We will come to what is adaptive optic system. So basically, this is going to be a world-class instrument in the next decade. It is So what do I mean by all that resolution and those numbers which I showed to you? Now here what we have is on the right is the image of Jupiter's moon Io. Io was observed by Galileo spacecraft at 500,000 kilometers. That is at a much smaller distance compared to us, and it has a resolution of 10 kilometers, which means to say that whatever is within 10 kilometers, we will be able to image on this IO clearly using Galileo. So this is a simulation has been degraded with respect to the TMT resolution, and in comparison we have the Keck resolution. So with TMT sitting here on Earth, we will be able to resolve like 30 kilometers at IO distance. So that is the power of TMT, and you can see very detailed features, unlike Keck, and not as best as Galileo, but better than much better than Keck telescope. So here is a small movie showing the light path of the telescope. So the light from the celestial objects are parallel beams. They hit the primary mirror surface. They get reflected onto the secondary mirror, and from secondary mirror, the light falls onto the tertiary mirror, which then directs the light into various science instruments on either side of the telescope. These two platforms are called Nasmyth platform. So this is so this primary mirror, what you see is 30 meter. The secondary mirror is again a convex hyperbola mirror of 3.1 meter diameter, and the tertiary mirror is a flat mirror of size 2.5 meter by 3.5 meter. So this particular telescope is has a segmented mirror design. It is good at precision control. It controls highly precisely in nanometer scales, and the adaptive optics system is also the best in this. So the state of the instrument is also being built on this telescope. So what does all this mean? First, let me come to the adaptive optics technology. So I have a short movie over here. So why do we need adaptive optics? We have um, we have our atmosphere. It is an important aspect for humans or the life to flourish, but it is not so good for astronomers. This atmosphere bends the light or distorts the wavefront coming from the celestial objects. As you can see on the left side, what is happening as the light enters, the wavefront is distorted due to the presence of the atmosphere. This distorted wave gives a blurring effect, as you can see in the movie on the right side. So once you correct for this blurring effect of the atmosphere, what we get is a very sharp image, and that is done through a system called adaptive optics system. So what happens here, I'm going to briefly say. So if you don't have an adaptive optics, this is how the Neptune would look like. Now, what is the adaptive optics in a very brief way? I'll just say. So adaptive optics system, first we collect the a distorted wavefront. Then we, using the deformable mirrors, we anti-correct these deformations, and we pass it and collect the light. So once these deformations are corrected using the deformable mirrors, then we have a parallel wavefront coming over here. This is done over a loop, closed loop within the system. So this is the adaptive optics technology. As you can see, once you get a corrected image, you get a very sharp image. So that is the adaptive optics technology which the telescope uses for getting very sharp images, or the resolutions I spoke about. Now coming to the primary mirror design itself. So the primary mirror is not one single mirror. It is made up of 492 segments. So as you can see on the right side, the whole diameter is 30 meter, but each of this is a segment attached together. So there are 492 segments. These segments are 1.44 meter in edge to edge, while the thickness is 45 millimeter. So that is the very small glass. So this is a glass plate, and it is a zero expansion glass. It is from the company Ohara in Japan, from NAOJ. Clear CSM. ZHS is the name. So mounted on this particular mirror segment will be mounted on a segment support assembly, which will have several components which will be able to correct for the disturbances created due to wind, thermal or vibrational disturbances during the observations. So that's why this segment support assembly is a very important component of the primary mirror system. So this is how it is. You have primary mirrors closely spaced. The spacing between the two mirrors are like 2 millimeter, and what you see below is attached with the segment support assembly. There are 3 actuators for every assembly for tipping and tilting, and also moving up and down the segments to correct for the aberrations due to several of these factors I mentioned before. So that in itself is a very important technology. So you should understand that 30 meters is not a single mirror. It is many mirrors placed together so that it acts as a one single mirror. So primary mirror forms the heart of the telescope. So as I told you, the accuracy of this primary mirror should be very good. So how do you make these primary mirror segments and attach them together? So as you can see here, what we obtain from Japan is roundels. We call them, they are round glass plates of 1.52 meter in diameter. They are then there is a stress mirror polishing and grinding has to be done on this mirror, and then they have to be cut in the form of a hexagon. There should be pockets. It should be pocketed so that the edge sensors and other components can be attached to the base of the mirror, and the SSA mounted system looks like this. So this is one complete PMA, primary mirror PSA, primary segment assembly. So so what is India contributing is, of the 492 segments plus 82 segments, India is contributing about 82 segments of this primary mirror segments. So just a thing that there is a stress mirror polishing technique, which I don't want to go into detail, and you can look up into books. So how do you get this high accuracy surface accuracy mirror? Is that you apply stresses at the edge of the mirror, you bend it elastically, and you polish the mirror, you release the forces, the stresses you have applied, and it takes the required shape, as you can see here. So the accuracy we are making to this mirror is like 2 micron peak to valley surface errors. And the final step will be ion beam figuring, which will be done at USA. Once we send the whole system, it will be dismantled and ion beam figuring is done. And this is the last step to make the high surface accuracy primary mirror, and that will give a peak to valley surface errors of 2 nanometers or less than 2 nanometers. That is the kind of accuracy we would require on the primary mirror segments. So since this is the week for celebrating women, and also to uh, encourage women to get into science, this this particular work package, the lead is Professor G.C. Anupama, the Dean of Indian Institute of Astrophysics. There are two other women engineers who are involved in making of all this. One is uh, Miss Janani, and the other person is Miss Vaishali. So I mentioned them here. It's not that only these three people are working. With apologies to our male colleagues, since this is the Women's Week, I just want to highlight that there are women working in the forefront of making this high surface accuracy primary mirrors. So then another aspect which is important for controlling of the whole 30-meter telescope is the software. The whole telescope or the whole observatory needs to be controlled by a software, and major part of the software is being given by India. And from ITCC or from Indian Institute of Astrophysics, India TMT Coordination Center. So we have three women working towards the software development. What we basically give is the observatory software and telescope control system is being developed currently in India. So again, these are Dr. Smita Subramaniam, Ms. Rajalakshmi, and Director of Indian Institute of Astrophysics, was previously involved with this, and she is Professor Annapurni Subramaniam. So I just want to give the brief. So we have now a primary mirror. We have a very good secondary and tertiary mirror. Now the light is being directed from the tertiary mirror into the instruments. So what these instruments are going to do? The instruments are going to take images and spectra of celestial objects. So here I show one of the first light instruments, which is the wide field optical spectrograph. The name is here. So the PI is from Caltech, Professor Charles Tidal, and the project scientist is Eric Peng from China, KIA, PKU. So this is how the WFOS instrument looks, and this is still in the design part, and this is in comparison to a human, what is the size of these instruments. As the telescope aperture increases, the size of the instruments, the back-end instruments also increases multifold. So this is just a illustration of that. So what is this instrument going to do? This instrument is going to take images and spectra in the optical wavelength range, that is 0.31 to 1 micron. It is a seeing limited instrument, which means the light is not corrected for the atmospheric disturbances. The light, however, comes through the atmosphere, is taken, and this is basically used for large field of view. So we can observe about 60 to 100 galaxies at simultaneously in one go. So this gives a resolution of about 50 milliarc second per pixel, and we can also take a spectrum of various galaxies and stars, and the resolutions in various resolutions, basically low, medium, and high resolution spectra. So India is contributing substantially to this WFOS instrument as well. So the um, mechanical design of grating system, of filter system, of camera rotation system is all being done in India. And there is a calibration system also, which is being optomechanical design is being done by India. So the whole WFOS instrument control software is being built, will be built in India, and the electronics design currently we are trying to attempt for the whole of this instrument. Again, there are there is a significant contribution from women scientists. We have here Professor Shivrani, Ms. Devika Divakar, and myself contributing to the development of design and development of the instrument. The next instrument I want to speak about is the infrared imaging spectrograph, which we also call as IRIS. IRIS is a diffraction limited instrument, which means to say that its light is going to be corrected by the adaptive optics. So it will be able to produce very sharp images of stars or galactic center of it will be able to make substantial contributions to the supermassive black hole research and other things. So the light to the iris is not coming directly from the tertiary mirror. Instead, it gets in the light is directed into the adaptive optic system of TMT, which is called NIFARIOS, Near Field Infrared Adaptive Optic System. So this is the optomechanical design of the system. As you can see, it is quite complex. It has a deformable mirror, which is an important part for correcting the atmospheric turbulence, the disturbance. So the contribution from the India side is a minimal in this particular instrument. But I would like to mention that the women scientists involved in this particular instrument are quite large. For example, the project scientist is Shelley Wright of UCLA, and the optics design is being led by Professor Reni Kupke of UCSC, Santa Cruz. So this particular instrument will be able to look at several objects, but important of them is it will be able to give information of when did the first stars and first galaxies form, which you can see on the right is a simulation of how the galaxies might have, galaxies and stars might have formed earlier in the early universe. So next important contribution from TMT is going to be from the second generation instrument. These instruments are not going to come with the first light. They are going to come a few years later. So this is a high resolution optical spectrograph. A happy thing about this instrument is that the PI is or the principal investigator or the main design will come from India for this particular instrument, along with partners from China, Canada, Japan, also getting involved in this. Then the next information is the planet formation instrument, PFI. That's also a second generation instrument. So we already know that there are about 4,000 and odd exoplanets. We have already detected exoplanets or planets from other solar systems. So what I show here is what is the how do we detect them? So first method, about 3,000 and odd exoplanets have been detected using the transit method. What you can see is you can see the dip in the star's light when a planet passes through it. So this is one of the transit, this method is called the transit method, and this has detected about 3,300 exoplanets. We also have detected the exoplanets using the radial velocity method, where the star wobbles or the spectral line wobbles because of the star rotating around the center of mass of the star planet system. And what this gives is the blue shifted and red shifted spectral lines. So basically the spectral lines keeps wobbling onto the left and right of the wavelength spectrum. So using this, we will be able to detect what is the kind of exoplanet and the mass of the exoplanet. So about 400 of the exoplanets have been detected using this method. But what will TMT do? TMT will be able to directly image the planets. So the central star has to be blocked. And this is a very short movie. The Let me explain here. The central star is very bright and it will be blocked using kind of a coronagraph. Kind of a plate which will block the star's light. Once the star's light is blocked, you can see faint planet uh, around this uh, moving around the central star. So this kind of high resolution imaging will be possible using TMT, and this will be possible for Earth-sized planets. So using Keck, people have detected Jupiter-sized, Jupiter-massed planets. Using TMT, we'll be able to go down to Earth-like planets. Also, we will be able to characterize the atmospheres of these Earth-sized exoplanets to be able to see if there are any life forms present. So another important area where the iris will play an important part is the black hole detection and measurements. In the center of our galaxy, there is a supermassive black hole, Sagittarius A star, and this year's Nobel Prize has been awarded to Andrea Ghez for the same discovery. The discovery was not easy. They had to wait for 20 years, where using simple Kepler's laws, they are able to measure that they are able to detect that there is a massive black hole sitting at the center, and they could able to get the mass of this black hole. So using adaptive optics, we'll be able to resolve, we'll be able to get sharp images, and we'll be able to do this exercise for many more stars. This was done for about 6 to 8 stars, but we'll be able to do for many more stars, and not only within our galaxy, but for other nearby systems as well. So that will be the power of TMT. And with this, I just want to tell you what are the opportunities for girls. Um, this is a very serious topic. We all agree that there is a leaky pipeline problem where uh, where though the enrollment in the primary stage is equal, like 50%, 50% of boys and girls are enrolling, but when it comes to the final stage, we have a lot of trained technical people losing out, especially women. So we have to understand why. There could be several reasons for this. I don't want to get into the reasons, but we have to address this issue. Having said that, what I want to mention here is that India TMT, the percentage of women working in India TMT is not very high, but it is not low. It is like 21 to 22%. That is kind of the best average in the country. Uh, uh, so India TMT is open for women students, women girls, and I flash here again all the women working. So it is about 22% when compared to men. So how can women students contribute? So there is a TMT Early Career Initiative where graduate students and postdocs, they partner and work with different partners within the TMT. So it's a year-long collaboration, as you can see here, TMT Early Career Initiative. So workshops will be having several design challenges which the students will be able to work out, Then once the workshop is over, they can go back to their country and continue collaborating with these scientists. And once there is some fruitful results, they can come back to any of the TMT partner institutions to do an internship. So this is for uh, graduate students and BTech, MTech kind of students as well is possible. So the internship at Indian Institute of Astrophysics and India TMT is also possible. Internships like 6 months to a year is possible, and workshops like the techie workshops are there, ASI workshops are there, where you can get um, initial hands-on experience on what is exactly going on and what is required. So that is a kind of a training what you get, and once you get the training, you can continue working with the India TMT, the scientists or engineers in various aspects. Another way to get into astronomical instrumentation is via MTech PhD, which the Indian Institute of Astrophysics offers. And if you take up a subject of TMT related, you are able to work in IIA, IUCA, or ARIES. So there are several postdoctoral opportunities as well for people who have finished PhD and trying to do some hands-on instrumentation. So there are postdoctoral opportunities as well. And so I request all of them to visit the TMT website, India TMT website, and also the IIA outreach and IUCA outreach pages for other information. So this is one way of entering or working with TMT. So it's not only BTech, MTech. We can take intern students of bachelor's, master's, master's, bachelor of science, and other streams as well. So yeah, I don't want to get into the details of why we have the leaky pipeline. I just want to stop here and take questions if there are any.
Okay, thanks a lot for this wonderful presentation. And also, I want to thank all the participants for being patient. We have around 80 participants in total. I will first invite questions from the participants who are connected through Zoom. If anyone has any question, they can raise their hand and we can take up the question. Or alternatively, they can put the questions in Zoom. Okay, Parth has some question. Tejas, you can unmute yourself and then ask the question.
Can I speak in Hindi? Is okay?
Yes, yes, yes. You can ask in Hindi.
मेरा मेरा एक क्वेश्चन नहीं है, मेरा सवाल नहीं है, मेरा एक सुझाव है कि इस तरह के जितने भी वेबिनार होते हैं वो क्या आप रिकॉर्ड करके यूट्यूब पे डाल सकते हैं? अगर यूट्यूब पे डालेंगे तो ज़्यादा से ज़्यादा लोगों को इसके बारे में जानकारी होगी और ज़्यादा से ज़्यादा लोगों को ये जानकारी पहुंचेगी और आएंगे इस फील्ड के अंदर। खासतौर पर लड़कियां भी इसके अंदर आएगी।
Okay, we have one question on Facebook. Can TMT also be used for gravitational lensing method to detect exoplanets?
Sorry, I had muted. Uh, Gravitational lensing is nothing but the bending of light due to the presence of a very massive object. So, this gravitational lensing effect can be used um, to detect very far off uh, or early universe objects. So, um, yeah, so it is possible to use the gravitational lensing to detect a very far off object.
Okay, I'm moving to the next question. How accurate is the data which are getting about exoplanets, which are some light years away from us? And the second question is how much time is required to identify the composition of that particular exoplanet?
Um, so how accurate the data is depends on the how well we are able to measure the contrast ratio between the uh, star and the planet. So primarily the instrument is able to or the aim of the instrument will be able to um get a contrast ratio of 10 to the 8 between stars and exoplanets. So, somewhere between Jupiter to Earth sized planets will be able to measure. I'm not exactly sure about how accurate, but it will be possible to measure.
Okay, the next question is how TMT can help us to detect dark matter, if it can.
So, yeah, so one of the aims is to do IgM tomography. That is you there is a um, high redshifted quasar, and we try to observe the quasar light which is trying to reach us. It will pass through different medium. Then, using several of such observations, we'll be able to map the foreground uh, galaxy structure or foreground dark matter structure. So that is how we'll be able to understand about the dark matter distribution uh, mm, mm, in the universe. So we need to observe several different galaxies and quasars at a very high redshift, and we have to the light which comes through the intervening intergalactic medium will be able to give signatures about what kind of material is there between the medium, and this will help us to uh, map the dark matter structure or the large scale structure of the universe.
Okay, among our Zoom participants, one is asking, is TMT so beneficial with respect to its cost?
It's its cost. Um, the science gains are the discovery space which the TMT brings in is quite large. So we'll be able to understand not only about our own solar system, especially one of the science cases um, is to be able to study Kuiper belt objects, which may have some signatures of how our own solar system has formed. Not only that, not only the close by ones, but to the farthest, how did the first galaxies and first stars form? How did they evolve? So, so the scientific gains is quite remarkable. Will be remarkable using this telescope. Um, yes, it is worth it. There is another question. What is the location of TMT by Rachel Kodian? Yeah, so the TMT is has selected two sites. One is it is going to be built either in Mauna Kea, Hawaii, or in or on La Palma or in La Palma, Spain. Both these sites are good. The best site is Hawaii site, but La Palma is also good. And it will be built in the northern hemisphere, that is for sure. The first light of the telescope is there are a few questions on the chat. Juma, can I answer them?
Yes, sure, ma'am. Yeah.
So Paul is asking when can we expect the first light of TMT? First light is expected, the construction is expected to start in a couple of years' time, and we can expect at 2030 around first light. There is another question, Sanchit Tayade, why we are using segmented mirror rather than non-segmented mirror? That's a very good question. So the largest segmented non-segmented, or we call it a monolithic mirror, is a 8-meter class mirror. And Subaru telescope of Japan has a single mirror. After that, after 8 meters, making larger and larger mirrors um, will sag because of gravity. Will making single large monolithic mirror is of 30-meter in size is not possible. So the segmented mirror design is selected. It is not the first to be done. Actually, the segmented mirror design has been already demonstrated in the Keck telescope, which is a 10-meter class telescope. It is having 36 segments uh, forming an effective 10-meter diameter. So this is not a new technology, but um, um, well represented across now. When can you expect? Yeah, that's fine. Tejas, please go ahead, unmute yourself and answer. Ask a question.
अभी आपने थोड़ी देर पहले कस्टर या पर्सर के बारे में बोला था। जब वो 30 मीटर टेलीस्कोप बनेगी उसके बाद उससे आप डार्क मैटर का ये करेंगे। तो मेरा ये सवाल है कि इस साल या अगले साल जो सूर्य ग्रहण होगा उससे भी हम लोग क्या डार्क मैटर के बारे में पता लगा सकते हैं उसकी रोशनी के माध्यम से? क्योंकि मेरा ये मानना है कि जिस तरह से धरती पे वातावरण में हवा है उस तरह से डार्क मैटर यूनिवर्स के अंदर है। अगर यूनिवर्स के अंदर डार्क मैटर है तो अपने सूर्य और धरती के बीच के अंदर अंतर है उसमें भी डार्क मैटर होना चाहिए। उसके पता लगाने के लिए क्या सूर्य ग्रहण एक माध्यम हो सकता है? वही मेरा सवाल है।
आपका सवाल बहुत अच्छा है तेजस। डार्क मैटर जहीं कहीं भी है और धरती और सूर्य के बीच भी है। डार्क मैटर सभी जगह पे है, पर जब सूर्य ग्रहण होता है तब डार्क मैटर का पता नहीं लगा सकते हैं शायद। इसके बारे में मैं नहीं जानती हूँ, पर मुझे लगता है नहीं पता चलेगा।
Yes, ma'am. What is the focal length for a telescope?
For this 30-meter telescope, it's a F15 telescope. The focal length is about 450 meters. The website link which I gave, lot of these informations are there. You can go through it carefully there.
हाँ, ये मेरा सवाल वो थोड़ी देर पहले पूछा तो वही है कि सूर्यग्रहण से पता लगाया जा सकता नहीं, अभी तक किसी ने किया नहीं, तो उसके अंदर आप सबकी मुझे मदद चाहिए थी। मैं सोच रहा हूँ अगले साल जो मुंबई में सूर्यग्रहण होने वाला है उसके अंदर मैं वो प्रयोग करने की कोशिश करूंगा। उसके लिए आप सबकी मार्गदर्शन चाहिए थे और मैंने खुद से 7 साल पहले घर पे टेलीस्कोप बनाने की कोशिश की थी। उसकी थोड़ी गाइडेंस चाहिए थी। बाद में मैं आपसे संपर्क करूंगा नेहरू साइंस सेंटर जी, तो और आपसे भी, ठीक है?
जी शुक्रिया।
Okay, we have one question. In future, will radio astronomy and space observatory take over TMT, and will the launch of numerous satellites affect it?
Can you repeat the question, please? Sorry.
Yeah, the question is, in future, will radio astronomy and space observatory take over TMT, and will the launch of numerous satellites affect it?
The launch of numerous satellites will surely affect any observatory. Uh, yeah, so it is going to leave a terrible trails which can be totally uncorrected in the images, and we will lose out on detecting very faint objects. So definitely this definitely satellites, too many satellites is going to be a problem for ground based astronomy, but it doesn't mean that the radio telescope will take over the optical telescope. We want measurements of celestial objects in all wavelength bands. So it is not going to take over, but instead it is going to be complementary. Whatever the radio astronomy will be able to, or the radio waves will be able to detect, it will complement whatever is seen in the optical. So that has been always a complementary. Uh, uh, yeah, the wavelengths have been always complementary to each other. Will help each other. Yeah.
Okay, so we have reached the ending of our lecture. I have really enjoyed it, and I hope the participants who have participated here and asked questions, interacted with you, have also get some information about this. So I want to thank all the participants, both in the Zoom and Facebook, and I want to thank Dr. Sethuram. Thank you very much for joining and being patient. And I'm extremely sorry for this technical glitch at the beginning. And I want to thank you, and we look forward to collaborate you in future as well. Thank you, ma'am.
Thank you. It was a pleasure.